Hello, I'm Ray, the Ray in the Ray Code. In this video, I'll be going over the structural design pattern known as bridge. I use C++. Now you can find this design pattern in other programming languages, but this video is dedicated to C++. Now you can find timestamps in the margin so you can navigate to the section you desire most, because I go over why you should use this design pattern. You have the UML, I have some code sample, and also go over a SWOT analysis. So it's all there. Tell your friends about the Ray Code. You can find me on the Facebook page, and also on the X, and also on LinkedIn. Most of all, be awesome. Why is a structural bridge pattern important to the C++ developer? The bridge pattern is a structural design pattern that's all about decoupling an abstraction from its implementation so that the two can vary independently. This pattern involves an interface or an abstraction-based class which bridges the functionality from the concrete classes. Flexibility. One of the key benefits of the bridge pattern is the added flexibility. It separates two layers of abstraction, which allows you to extend and adapt them separately. This is particularly useful in C++, where multiple inheritors can introduce problems, and you rather compose objects rather than inherit from multiple sources. Avoiding exponential class explosion. Consider a scenario where there are m operators and n implementations. Without the bridge pattern, we might end up with having m times n combinations, which can lead to an explosion in the number of classes. With the bridge pattern, this is reduced to m plus n, enabling independent evolution. The abstraction and its implementation can evolve independently without affecting one another. For instance, if you have a UI abstraction and different platform-specific implementations, changing the UI abstraction will not necessitate changes in the platform-specific implementation and vice versa. Reusability. The implementation details are isolated and can be reused across different abstractions. Principal adherence. The bridge pattern adheres to the principle of composition over inheritance, which is a powerful guideline in object-oriented design. This principle is especially vital in C++ to reduce complexity, improve modularity, and facilitate more maintainable code. In summary, understanding the bridge pattern is crucial for a C++ developer because it provides a mechanism to keep the abstraction and its implementation decoupled, allowing for a more modular, maintainable, and flexible software design. UML for the pattern structural bridge for a C++ student. Abstraction defines the high-level interface that the client uses, holds a pointer or reference to an implementer, delegates actual work to the implementer object instead of doing it directly. In C++, often implemented as a base class with virtual functions. Refine abstraction extends abstraction with more specific behavior. Uses the inherited implementer pointer to perform operations. Delegates actual work to the implementer object instead of doing it itself directly. In C++, typically overrides virtual functions from abstraction. Implementor defines the interface for the implementation classes. Provides low-level operations that abstraction relies on. Does not need to match the abstraction interface exactly. In C++, usually an abstraction-based class with pure virtual functions. Concrete implementer A implements the implementer interface with specific behavior. Provides concrete definitions for all required operations. Can vary independently from other implementors. In C++, overrides all pure virtual functions from implementer. Concrete implementer B provides an alternative implementation of the implementer interface. Implements same operations differently than concrete implementer A. Allows switching implementations at runtime via pointers. In C++, used interchangeably through base class implementer pointers. Client interacts only with the abstraction interface. Does not directly depend on concrete implementation classes. Supplies or selects a concrete implementation implementator to be used. In C++, typically creates objects and passes implementator to abstraction. Abstraction, the main interface your program uses to hold a pointer to the implementation. Redefined abstraction, a specialized version of abstraction with added behavior. Implementor, the interface for low-level work, defines what implementations must do. Concrete implementer A, one specific way to implement the low-level operations. Concrete implementer B, another interchangeable implementation with different behavior. Client, the user of the abstraction wires everything together using pointers. Coming up next is the code portion of this video. You can find the code that I use in this video at my GitHub site and also at my websites. Most of all, tell a friend. Also, leave a comment of what you think if you got this far. Hello, my name is Ray, and I'm the Ray in the Ray Code. In this show, I plan to give an example of the bridge pattern, which is a structural design pattern. The first class I will add to our project will be the implementation class. Here we have the class structure. We include the IO stream at the top. We have a public deconstruction method for the abstraction class. We have a virtual operation implementation. Now let's create the abstraction class. At the top, we include the string library and we have the class structure. We also include the implementation class. We have a protected implementation pointer to hold the implementation. Next, we have the abstraction, which is extended with the abstraction class. We have the deconstructor for the abstraction, so we have proper cleanup. We add a string operation that returns abstraction-based operation with the implementation that we just passed in. Now let's create a concrete implementation A class. We will extend it with a public implementation class. We add an operation implementation which returns a string message concrete implementation A. Here is the result of the platform A. Let's create the concrete implementation B class. Here is a class structure and we include implementation at the top. So we extend this class with it. As a result, we require a method operation of which we return the string extended abstraction, extended operation with operation implementation. Now let's add the extended abstraction class. We start with the class structure and we include abstraction at the top. With abstraction, we extend this class. We pass in a pointer to the implementation and we return the string extended abstraction, extended operation with the operation implementation that was passed in. Now let's go to main for our demo. At the top, we include string, concrete implementation A and B. We no longer need the IO stream because that can be found in the implementation class, and we include the extended abstraction. We create some client code to return the operation call on the abstraction. We set up an implementation pointer to a new concrete implementation A and an abstraction pointer to a new abstraction with the implementation passed in. We pass the abstraction into the client code and do some cleanup. Let's set up another implementation we call concrete implementation B and pass the S abstraction into the client code. We do some cleanup and I think we are ready to run. We get abstraction-based operation with concrete implementation A. Here is the result on platform A. Extended abstraction, extended operation with concrete implementation B. Here's the result on the platform B. My name is Ray, always code with a smile. SWOT analysis of the bridge design pattern for C++ students. S. Strengths. Decouple design. Separates abstraction from implementation, making the system more modular and adaptable to changes. Reusable components. Enables reuse of implementation class across multiple abstractions, reducing redundancy. Scalability. Simplifies adding new abstractions or implementations without altering existing code. W. Weakness. Increasing complexity introduces more abstraction layers, complicating smaller systems or prototypes. Setup challenges requires careful design to correctly structure abstraction implementation hierarchies. Debugging overhead. Tracking issues across multiple layers can be more challenging in large systems. Opportunities. Core platform development. Ideal for creating portable libraries that separate platform-specific implementations from core logic. Graphic engines. Frequently used in C++ game engines for rendering abstractions and backend APIs like DirectX or OpenGL. IoT systems. Fits modular IoT design where devices interacts with varying protocols. Threats. Performance concerns. Overhead from abstraction layers might affect high-performance applications. Over-engineering risk. Misuse in simple scenarios can lead to unnecessary design or complexity. Alternate solutions. Adapter or composite might handle certain use cases more effectively. Well, that was my video. I hope you enjoyed it. You can find the code at the GitHub site. Also, find me on all the social media platforms like Facebook, X, and LinkedIn. Most of all, tell a friend because the free code is awesome.